Okay, this is like my fifth take on this. I don't know if I'm going to publish my previous takes where I kind of meander off on tangents, but this Mazzilli ZVS circuit, this I found in short from this guy Doom 2 Pro or whatever. That's how I found this video. You're gonna have to like scroll down here and find this so that you can go to this place so that you can copy first this and then this whole thing, these text files, over into Falstadt by using this twice. So you can paste it here and then open up the next one and copy it in and paste it here. That'll bring a circuit up similar to this. But if you want to see this thing exactly, you're going to have to go, because this is set to wattage at first, so you'll have to actually, oh shit, I just fucked up. Well, you'll have to actually go bring this up and switch it from power to current. So, if you do that, then you can get this display, so you can display voltage and current or power, but you can't do them both at the same time. But anyway, that's the modification I've made here. Plus, I actually took, this graph here of this voltage here. So, because I put a voltmeter on this, so I can actually see what voltage is actually across this coil slash capacitor, and then I made a graph of it. So I added this, by basically selecting this thing, the view in undocked scope. So that brings this thing up. So those are the modifications I made, but I didn't modify the circuit at all. You can ignore these components that say, M, that means milliohm. This is just them trying to simulate real world components as opposed to being completely ideal, but you can ignore these. So this really is just a tank circuit. This, ignore this, just assume this is a capacitor in parallel with this transformer coil. And it's important to have this model as a transformer, otherwise it won't simulate right. You'll get this if you model this as two separate inductors that aren't coupled. So, it looks like an electrocardiogram or something. I don't know if this would be the case in real world, but it probably would be something freaky, because these really should be, connected. They should be not just series electrically, but actually magnetically coupled too, so that they operate as a proper, tank oscillator. So, which is really a Hartley oscillator is what it is. But you want them to operate, as a single inductor with a center tap on it, not as two separate inductors that happen to be connected together. Otherwise, you'll get this result, which is how it should work, as opposed to that garbage you get over there. And note too, this is a 15 nanosecond simulation. I don't know if you need to, the other one was like 5 microsecond or something. I don't know if you need to have that high resolution on this or not, but you can play around with it. Anyway, this basically it was a little tricky to understand, because what I had to realize is, obviously this is a tank circuit. That stood out. I've been in electronics for a long time, and that stood out, immediately. But what didn't quite stand out is, okay, how does this really switch? My background's mostly microprocessors and digital electronics and all that stuff. It's not really been in the analog too much. I'm trying to actually, refresh my memory on some of that crap and really get more into the analog side these days. So I'm trying to understand things like this more deliberately. So this basically is a tank oscillator. You can look at it as a tank oscillator that happens to be kind of fed from the middle. But there's a few things that, epiphanies that you need to have. One is, okay, if you have current like flowing, let's say this transistor we're on, so that you have current coming from your positive, you can ignore this. This is just a choke. It's not important for the operation of the fundamental operation of the circuit as far as oscillation and shit, so just ignore that. and this is the positive of the battery, and this is the negative side of the battery that goes to ground. So you got a positive applied here, and then when this transistor is on, let's say it arbitrarily is the first to turn on, and this is off. So this actually, and again, ignore this 70, that's 70 milliohms, so that's like, again, I think this is in here just to simulate a real-world circuit, but it's not in here for the, you don't need this for the operation. You're going to have to come up with like a 70 milliohm resistor. That's already, they're figuring it built into the, that's the RDS on, okay? So you could actually take this out and have it work as an ideal component, I suspect. I don't think this or these two things are necessary, because this isn't real either. I mean, you can just get rid of this, because that's, like an ESR, equivalent series resistance inside of a capacitor. But just ignore this and ignore these two things. So if this was on, okay, that means this is shorted to ground, okay? So that means this will be just above ground potential, which you can see here, it's 1.47 volts, alright? And this one, is off. It's got 67 volts across it, as you can see down here. So, and you can see what's going on with the waveform. This is basically the voltage current, across this transistor, and this is the voltage current across this transistor. So, and this is the output. He's actually, see, that's this wire here he's displaying the waveform on, and this is the output of the resistor, the current going through it, and this is the voltage on that transistor's gate, and this is the voltage on this transistor's gate. So, just to tell you what's going on here, this I added this voltmeter across the coil / capacitors, across the tank circuit. So this is an inductor in parallel with this capacitor. Ignore this. Okay, it's a tank circuit. This is the voltage across it, and I actually graphed it, by using this view and undock scope. That allows you to have a little thing you can move around like this, which you can, go have independent settings of by hitting properties. Anyway, the point is that, okay, you got this tank circuit, and this transistor's on. Okay, this point is at ground, while this, is at a high voltage. Now, the voltage this is at, is basically dependent on what voltage is across this capacitor here. So you got to realize that, alright, while this transistor is on, okay, ground, and again, one of these transistors is going to, when you first turn this thing on, current will flow through this. Again, ignore this. This is irrelevant. That choke's irrelevant to the operation of the actual circuit. But let's see, you got current flowing through this, because this one just arbitrarily happens to be the first one that turns on. When this is on, this is off. And when this is on, this is off. Both of these cannot be on at the same time, and by any stretch of the imagination. And both of these cannot be off by any. They're mutually exclusive. They can't be off at the same time or on at the same time, because when this is on, okay, that makes this voltage low, which allows current to flow through this diode to ground, which does what to this voltage at the gate? Because this gate, if you know anything about FETs, it's got to be, this particular FET is an N-channel FET, it's got to be high, in other words, a higher voltage than ground, at its like source or whatever. But basically, you got the VCC, this case 12-volt battery, as you can, or 24-volt in this case. It's going through here, and basically is going through that diode straight to ground. So that means ground, plus 0.6 volts or whatever, and this is a little above ground because it's not 0 ohms, but I mean roughly 1 volt or so. In fact, you can see in this case it was 2 volts at this point in the circuit, that's basically keeping this thing essentially off, because the voltage is too low. The voltage needs to be much higher to get good conductivity out of this thing. So it's essentially off at this point. Whereas this voltage is, look down here, it's at 12 volts. Okay, and that's because we got this 12 volt reverse bias Zener here. So it's acting like a little bitty regulator is what it's acting like. So it keeps that to 12 volts and no higher, so that this doesn't blow these FETs out, because usually these are, it's a no-no to usually put more than 15 or 20 volts across a source gate of the FET. So of a FET, they're kind of sensitive to that. But that's across the gate and source, but not the drain and gate or the drain and source. Those can be much higher voltage, like this is a 200 volt transistor. So you can have 200 volts across these terminals here and 200 or more across the drain and the gate. But the gate and the source, you have to keep that under control. That's why they have this regulator here, just so it doesn't fry the damn thing. Then they have this 10K resistor here, which acts like a voltage divider. So if this diodes, these two diodes, like this one and this one, I really wish you would have drawn this up here. It makes this less confusing, this diode, because it's associated with this transistor. So it would be nice if this were up here, but I could redraw it, but I mean, fuck it. Any rate, if we just ignore these diodes, well, this would just form a voltage divider here and a voltage divider here. And if these diodes, if you took them out, well, then you could actually have these on at the same time or off at the same time. But because these diodes are here, you cannot have them on or both off at the same time. The diodes make it so that, if this is on, this voltage is low. Like you see here, it's 1.4 volts. Okay, and that makes current flow through this diode, keeping this relatively low at 2.3 volts. Okay, whereas this diode is not conducting any power because it's at 67 volts there and at 12 volts over here. So that means that this transistor is on because it's got 12 volts across it, which is a good operating voltage for this FET, whereas 2 volts is a bad operating voltage for this FET. So it's effectively off, meaning the voltage across it is high because its resistance is high at that point. So that's why this voltage is 67 volts as opposed to this voltage being 1.4 volts, because this is on, making a low resistance path, like 70 milliohms low resistance. Although in practice it probably won't be that exactly, but at any rate it makes a low resistance path to ground. But because we have these diodes connecting up the two, this voltage controls this transistor's gate voltage, and this one's voltage controls this transistor's gate. So again, the key is this works backwards though. When this is conducting, that means this transistor is off. When this diode's conducting, that means this transistor's off. But whether this diode's conducting or not is controlled by this transistor, and whether it's on or not. When it's on, this is conducting. That means this is like, too low to operate the transistor, 2 volts. Okay? Whereas when this diode's on, well, or when this transistor's on, this diode's conducting because this becomes very close to ground. So basically, it's siphoning power away from this voltage divider. Basically it's short-circuiting this resistor is what these diodes are doing. This one short-circuits this resistor, this one short-circuits this resistor. It's one of the reasons this resistor is such a high value, so it's easy to short-circuit. So it's not hard to overcome a 10K resistor when you're talking about a fucking diode here. And two, by the way, you could probably actually use just regular 1N 4007 diodes, as long as this thing's not going to run at more than 10 kilohertz or so, because they'll operate just fine, typically at those levels. But but you know, you're not dealing with a lot of current, because all you're doing with these diodes, by the way, is you're really, you know, not just trying to, you know, drop power across a resistor, but you know, these FETs actually operate, this gate and source, you know, tend to act like a capacitor. So when you turn a FET on, you're actually having to charge up a capacitor, and you know, it's like the Miller capacitance. You know, look into it. But you know, there's actually what they call a Miller plateau, and once you hit that Miller plateau, the voltage will not change across the thing until that capacitance is charged up, and only then can the FET turn on. Okay, but until that capacitor is charged up, the FET can't turn on. Okay, so that's why this resistor is so small, is so it can charge up that capacitance really quickly. So you know, you got positive here, negative here, because this is ground. Again, ignore that. But 70, you know, 70 milliohms here. So basically, you're trying to charge up the capacitor, which is pretty small, but it does take, you know, if you're running this at a high frequency, that's a significant time factor. So, you know, you got this Miller capacitance, and then you got this resistor here, so it's an RC time constant thing. So it takes 5 RC time constants to charge this thing up. And basically, it's as simple as that, but until that capacitance is charged up, more or less, you know, to some intermediate voltage level, this FET can't really turn on properly. But when it's below that, you know, the capacitor is not charged up, okay, the FET, you know, will be off. So, at any rate, that has a lot to do with how, you know, how to turn on a FET. But if you want to turn it off, you also need a path like this to ground so that this capacitor can discharge. Because believe it or not, a FET won't turn off until you discharge that Miller capacitance. So again, it's like a small little capacitance, and you know, until you discharge it, and that's where this diode comes in handy. It not only keeps this voltage low, but it's a discharge path for that capacitance. So it can go, you know, basically discharge itself through, you know, in a circuitous way through ground. So, you know, because it's going right here to ground, when this is on, you know, it'll be able to discharge this, so it'll fully turn off. But that's why really you're going to find that, you know, this will turn on, and while this is still on, you know, you won't see that these two are in exact alignment. Like when this, you know, see, this yellow thing is the current, and this blue thing, or the green thing, is the voltage across the transistor. And don't ask me why these fucking things can't be made the same size, because they are 71 volts peak, 71 volts peak essentially, but they don't look the same height. That's a bug in this fucking software. These really should be identical, just out of phase. But at any rate, the point is that, you know, when you got you know, this transistor's on, this transistor will still be on too until that Miller capacitance is discharged. Okay, but it'll have to discharge, you know, basically through this, you know, wish this guy wouldn't have drawn this like this, but through this diode through ground, okay, which remember at the time, since this is still on, it's still, you know, it's still got ground here, okay, but the capacitors and the transistor's in the process of turning off, but it can't turn off until that capacitance is discharged. So until it is, both of these are going to be on at the same time, very briefly. Now, there isn't really a shoot-through current here, because this isn't like a CMOS totem pole, so you really don't, or an H-bridge or something, you really don't have shoot-through, because this is ground here. Okay, this isn't like a load's connected, this is ground. So it really isn't a shoot-through situation, because these two can't short circuit through each other because there's ground in the way, okay? So them being on won't act at the same time, won't really destroy both of them like it could in a shoot-through situation. You know, if you had a CMOS totem pole, look into that if you don't know what I'm talking about. So this isn't like that. It kind of resembles that, but it's not like that. So that can be confusing, you know, if you're not used to this stuff. But yeah, there's no real danger of shoot through here, but it's still, these could be on at the same time. both drawing power at the same time, which is kind of a waste because, you know, really you don't want that. That's kind of, I think, why these waveforms look so funny on these current waveforms. It might have something to do with that, I don't know, but you know, the point is that, you know, again, when one turns you know, basically on, the other one's not necessarily fully off yet, so there's a little bit of an overlap while the capacitance discharges. But at any rate, that affects the switching speed, how fast you can switch on or off one of these transistors. Now, because of this capacitance. Now, interestingly enough, if you actually had a constant current source driving this thing, it would actually charge up at a linear rate, so it becomes really, really easy to predict. So if you're ever using like a constant current source driver, like in an LED application, for example, that has CCS drivers in it, you'll find that it's easy to calculate these things because it's a constant current source. So, you know, it can't draw any more current than that CCS will allow, because, you know, so that this charge curve actually becomes very linear when you have something like this powered by CCS. So that's just an aside, but you know, it's just a point that this really is a genuine capacitor. So it's actually a real capacitor. It's not some, you know, because it's basically, you know, got a glass oxide layer. It's vitrified. So this junction, these aren't electrically connected inside a FET. So it's like a little plate of a capacitor, and yes, it has indeed capacitance on it across it. So, but at any rate, that affects it. But you know, like I said, because of the presence of these diodes, it cannot, this transistor cannot be on at the same time as this one. Again, if we remove those diodes, they could be. You know, they could be totally independent. It wouldn't matter. In fact, theoretically, you could actually have, you know, get rid of these damn things and drive this with a 555 timer to where, you know, maybe two 555 timers, but a 555 timer and an inverter, for example, taking into account the proper, you know, sticking it through some resistors and shit so you can get it up to 12 volts. But I mean, you could theoretically drive this and have this one, you know, go on when the pulse is high, and this one go on when the pulse is low. Again, this one goes direct from the 555, and this goes through like a CMOS inverter with a transistor on it, that kind of thing. But again, you'll need some drive circuitry probably because of the currents involved. But at any rate, the point is you could theoretically control this with just a square wave independent of this and get rid of these diodes, and it wouldn't be oscillating, but you would be hard driving it, which wouldn't be very efficient, but you could theoretically hard drive it, and then you could control the frequency independently of whatever's going on in this. In fact, theoretically, you wouldn't even need this capacitor. You just need some freewheeling diodes. You know, don't rely on the body diodes. That's generally not good practice for these, but you know, you need a freewheeling diode across this to eat up the energy, but you know, then you actually could literally drive this with a square wave. Again, it wouldn't be efficient because most of the time, you know, you'd end up in a situation at a low frequency with a square wave is really not doing anything. I mean, it's just drawing current, you know, through the inductor for no good reason, and you know, it's not inducing a voltage into the secondary because that only happens when the current is changing. You know, but in a square wave, you can end up in a situation where, well, it's static, you know, because the current's not changing, it's square, right? So, I mean, at some point, this field will be fully charged up in this inductor, and once it is, well, you know, it's not going to do anything on the secondary, so you're really wasting power. But at any rate, I digress. That's if you think about driving this independently, which I still am, because I'm still wondering how important of a role, like in an induction heater, frequency would play to whatever it is you're trying to heat up. As it occurs to me, like there could be, you know, depending on the type of steel, for example, if you're trying to heat up steel with an induction heater, well, the type of steel, you know, it's going to have different grain structure, right? Well, it occurs to me that it could be that you know, different types of steel have different grain structures, so they may actually respond differently to frequency. It may be that some frequency might be better than others for efficiently heating that up, and unless you've got independent control of this frequency, you can't investigate that. You know, so it would be interesting, you know, having this separately controlled, so you could kind of see if that's true or not. It might be even a way of identifying different types of steels depending on what frequency you have to set it up at, as long as you don't heat it up past the Curie point or whatnot. But anyway, or certainly past, you know, the melting temperature for sure. But you know, otherwise this inductor and this capacitor is what sets the frequency here. So it really is just a tank circuit. It's 1 over, you know, 2 pi radical LC or whatnot. You know, it's the resonant frequency, so it's more or less in that ballpark. So you know, that's kind of the frequency this will oscillate at, you know, whatever your capacitance and whatever your inductance is. But since your inductance changes, okay, it'll change. You know, the inductance will change. For example, if you're using this as an induction heater, well, whatever you put into that field will change the induction, you know, the magnetic field in the circuit, and therefore change the inductance. So it'll affect the resonance. So the frequency will change depending on what you put in that coil. And you know, if it were driving like a flyback transformer for high voltage, again, if you're pulling an arc on the thing, that'll actually change the load on the transformer, which will change indeed the inductance on this thing. In fact, if you ever take just a plain Jane transformer, like a power transformer, and you take the primary, for example, and hook your multimeter up to it, or not multimeter, but I mean, it would work with a multimeter if you want to put it in ohms. So you can hook an ohmometer up to it and actually take a potentiometer and put it on the secondary, short circuit the secondary with a potentiometer, so you can vary the resistance. You'll actually see that reflected in the primary. And if you actually put an inductance meter on the primary and a resistor on the secondary, believe it or not, you can control the inductance by varying the potentiometer. So, and two, it's definitely true that if you actually take a coil, you know, an air coil, like for example, you would have an induction heater, you know, with no load on it, you don't have anything inside the coil. If you take that and stick that on an LC meter, its inductance will change, of course, obviously, depending on whether you've got something metallic or not. Now, interestingly enough, the inductance will increase if you put something made of iron, you know, something magnetic inside of it, like steel or what have you. The inductance will go up quite a bit. But if you put something aluminum in there, the inductance will actually go down. So it's interesting because aluminum's diamagnetic. So, you know, I haven't fully looked into that, but again, you know, aluminum is affected by this. I don't know if it's affected in such a way. I don't know for sure if you can actually heat up aluminum in an induction heater directly, but I wouldn't be surprised if you could. But anyway, the point is, it's just an interesting little aside. But at any rate, since the inductance will change, you know, and again, same thing in a flyback transformer, because depending on whether you have the load or not, that will be reflected into the actual inductance of your coil. So it'll change the frequency of it, you know, because it changes the L term and the 1 over 2 pi radical LC thing. So so basically, you know, that's what's sort of going on with it. But this is what sets the frequency. But like I said, you could actually theoretically set it independently. But again, it's a little wasteful to do that. But it's just something interesting to look at, and I'm very, you know, interested in seeing about that possibility, at least for laboratory purposes. But at any rate, the key to this fucking thing working, you know, again, we've already established how these can't be on at the same time. You know, only one can be on at the same time. We've established that this is a resonant tank circuit. Now, the other thing, you know, that you need to keep in mind is that if I were to, you know, just ignore this, even though you could actually apply a voltage through this thing, and take the rest of this shit out, if I just took an inductor and put it in parallel with a capacitor, and I applied power briefly to it, and then removed that power, this would basically oscillate until, and you would see it die off. In fact, there's probably a circuit here that goes into that, I'll bet you. But passives, say 20, notch filter, Butterworth, comb, high pass. These are all filters. Other passives, okay. I'm gonna be pissed off at this thing. Let me save this stupid thing. Save as. Okay, and that downloads it, by the way, to your local computer in your downloads section, so you can reload it later if you want. Other passive, series parallel. Now, I think there is something like that here. I just can't see it right offhand. But at any rate, what you would... Yeah, what you would see if you had these connected in parallels, you would see it. It's being plucked, like being plucked by a guitar string, okay? You know, it takes it a while to die down. It'll start really high and then you know, start really high and then kind of peter out. But the point is that's something to keep in mind too, and that would happen at this frequency. That's resonance, okay? You know, in fact, that's kind of a way, in a way, if you wanted to actually measure the resonant point of a circuit, you can just take like a capacitor of known value and an inductor of unknown value, for example, because capacitance meters are easy to find. So if you don't know the inductance, you know, you can get an idea of the inductance by taking a capacitor and an inductor, okay, and, you know, like I said, actually apply power to it just temporarily, but then have a frequency counter hooked up to that, so when you remove power, it counts the frequency. That'll give you the resonant frequency, so you can actually kind of plug that in and use a little bit of algebra, and the F, you know, resonant frequency equals 1 over 2 pi FC, or LC, radical LC. You know, you can actually solve for L algebraically to find out what the you know, what the inductance, the ballpark of it should be. But remember, you're dealing with a real-world circuit, so it won't be exact, because real-world inductors and real-world capacitors actually have different resistances, and inductors, for example, have a little capacitance in them, and capacitors have a little inductance in them. So these aren't perfect, but it'll give you a good idea, you know, of what the value is, you know, because it will have a resonant frequency, and that is true. So you can find out the resonant frequency by just plucking it like that, you know, attaching power for a couple of seconds, allowing the fields to charge up, and then just quickly remove them. You know, remove the power to it, and it will oscillate at some frequency as you do that. So, and it'll take it a little while, but eventually it'll die off. So, but this circuit works with that principle in mind, that that phenomena that actually controls these two transistors. And that's the thing that was kind of hard for me to grapple with, is how is this actually controlling these two transistors? That's confusing, because, you know, if you look at this circuit, this isn't really connected to ground. Ignore this secondary, that has nothing to do with it. That's for the simulator. So again, you don't even have to have this deal. You would have this secondary here if you had a flyback transformer plugged into it or hooked up to it in some way, but you wouldn't have it with an induction coil, for example. There's no secondary, but this thing still works. But the point is that you know, you can pluck this thing, you know, now I've kind of lost my train of thought. But anyway, you know, this thing will oscillate when plucked, but basically this is, initially it's being plucked through the middle here, and you got current, you know, again, ignore this choke, it's not that important for the operation of the circuit. That just, you know, keeps the current spikes under control, is what it kind of does. But, you know, you got positive flowing through here, and let's say this transistor turned on first. Okay, well, since this transistor is on, basically this, just as you can see, is like at 1.47 volts. Down here you can see that, whereas this one's at 67 volts. Why is this at 67 volts? It's at 67 volts relative to this point. That's the key thing to remember, is that there's a voltage on this capacitor, and this transition actually happens when this value, this voltage across here that I'm measuring, this voltage across this LC circuit, when it gets to the point where it's crossing zero, you know, right across the middle here, that's when this transition occurs. And there's a reason for that I'm going to get to in a second. But you know, anyway, when you know this thing first turns on, one of these is going to conduct before the other. It just, you know, it's because no component is exactly identical, and because of that, one will win the race to turn on at the same time. So anyway, you'll have power flowing through, for example, this transistor, but they won't switch until this voltage speed this up a little bit. Okay, shit. But at any rate, you know, right when that happened, you know, this voltage changed. Okay, see, this is now at 2 volts, and this is at like 54 volts all of a sudden. Let's run it a little more. Okay, now we're getting to the point. Okay, now what's going on here, that's at 7 volts, and this is at 3 volts. Okay, so it's, you know, you can see as this voltage approaches 0, this is getting ready to change, and this, you know, you can see that, okay, this transistor here, you can see it highlight, you know, this transistor here is coming out of conduction because it's yellow, you know, because it was conducting, because you can see yellow here, the current that was flowing through it, the voltage was 0-ish that whole time, but the current was high. Here the voltage was high, but the current is 0-ish. So this is about to turn on. This is in the process of turning off, and this is in the process of turning on. You can see the current start to increase here. But where does this voltage come from? Okay, so basically, you know, when this thing is on, all right, you know, it crosses these transistors, change state. One becomes on, the other becomes off once this gets about to 0 volts. That's why I call it a 0 volt switch, because it actually happens when this voltage, okay, is at or near 0. Okay, now the thing you got to keep in mind is this is a tank circuit, and because of this, we're actually measuring the voltage not just across the capacitor, but across the inductor too. Because in a tank circuit, you know, basically the capacitor and inductor are in parallel. Because of that, the voltage across them will be in phase. Okay, but the current flowing through them will be 180 degrees out of phase. So that's just that's something to keep in mind. You know, the important thing to remember is that the voltage is the same. Now, in a series resonant circuit, the current is in phase, but the voltage is out of phase, and that's why in a series resonant circuit you can actually generate some really high voltages between the capacitor that's in series with the inductor. You know, and that point can actually develop a high voltage across any of those two, either of those two components. It can be thousands of volts if you have a high Q, but you know, that's something to, you know, that's a different story. But the point is that in a parallel tank circuit, the voltage across the components is in phase. It's the voltage across the capacitor is pretty much the same as the voltage across the inductor, but the currents can be different. In a series circuit, the voltages can be different, but the currents are the same because they're in series. So so that's just another little point of fact that's interesting to keep in mind. But really, we are talking about the voltage here and here, because the important thing to remember is that this capacitor and inductor are actually playing off each other. But when you see this approach 0, it actually is 0 volts across both of these components. I mean, both of them are actually at 0 volts. But the current tends to be maximum. In other words, at that point, the capacitor its current is actually changing at its maximum rate, trying to charge up the inductor, or vice versa, depending on how this thing's going. you know, because the inductor will charge up the capacitor will charge up the, you know, the inductor starts out by being charged up. It develops a voltage across it. Like, for example, you know, if you got current flowing through this side of the coil, okay, that's forming a voltage here. Now, as that's happening, a voltage is also forming here, by the way, incidentally, which is like, you know, for example, double this voltage. So that's one of the reasons you can actually get like 2 or more times the voltage across it, because this doubles. And two, if you realize that this is like a DC pulse you're putting into it, well, you can think of it as, well, if you're converting DC to AC, you got to multiply it by 1.414 if you're going from, you know, to try to find the peak from the average DC value. You can sort of think of this like that, that it's actually converting an average to a DC or an AC value. So it's, you know, you can think of it as being like 1.4 times the peak voltage here, which is double the applied voltage. So, you know, we get like 24 volts supplied to it, a 24 volt square wave. Well, that's 48 volts when you double it. Again, this is loose, but it's a way of thinking about it to try to understand why the voltage is high. But so if you get that, that's like 48 volts, but if you multiply that times 1.414 to convert it to a sine wave, basically it becomes close to the voltages we're seeing here, which is like, you know, 60 some odd, you know, 69 volts, for example. So, you know, that actually works out about right if you actually do the math, you know. Do it, 24 volts times 2 times 1.414, it'll come out to about the same voltage. So that could be a coincidence. I saw this Russian guy do a video on it talking about it being partly due to the first term of the Fourier transform, which it could be. I mean, that's not out of the question, but this is maybe true too. So I don't know, or maybe an alternate explanation, because this seems to work out pretty well. But then again, you know, you can see these voltages get even higher than that. But still, you know, that's 71 volts, so, you know, that's a little higher than, you know, I would tend to predict, because, you know, basically 24 times 2 times 1.414 is 67.8 volts. Well, this is higher than that. So again, the Russian guy may be right, but this may actually be a factor as well in that when you're looking at the physical explanation of where that Fourier term comes from, that may have something to do with it. I could be completely wrong, but it's just a theory of mine as to why this is about triple the voltage of your power supply. So according to that Russian guy, he said that's pretty consistent in all versions he saw of this, that is about 3, you know, approximately pi times the voltage, and he was wondering why that was. It was an interesting video and interesting work he did. I forgot, I got it, I mean, I got him bookmarked somewhere, but I don't know where it is. I think I got him in one of my playlists. But anyway, the point is that, you know, anyway, this forms, like I said, a resonant circuit. Okay, and this switching occurs once this approaches, you know, 0 volts. That's why I call it a 0 volt switch. Okay, but what's happening is again, you know, basically, you know, if we charge our inductor up with this current, okay, that'll form double the voltage across it, which once we, you know, the thing's charged up and the transistors change state, well, then it starts to oscillate, and it oscillates by taking the energy stored in this magnetic field and forming a voltage across it, so it tries to maintain its current flow. But it does that, but since there's a capacitor here, it actually sinks its current into this capacitor, which starts at 0 volts when it's the circuit's first turned on, but the capacitor charges up, the voltage increases, the voltage in this transformer increases. Again, it'll try to pump out whatever voltage it can to maintain its current flow. It's what it's trying to do, you know, by any means necessary. So it'll generate whatever voltage it needs to try to do that. But eventually it runs out of juice, its magnetic field runs out, and once that happens, okay, this capacitor is now fully charged, but this voltage will disappear across it as an electromotive force. You know, in other words, the inductor actually won't have a voltage across it anymore because it's spent. It's already transferred its energy into this capacitor. But at that point, the capacitor is sitting there running at full voltage saying, hey, I got this short circuit here, you know, this piece of wire, and I got all this voltage, this energy, you know, stored inside me. All these joules are waiting to get out. Where can I get rid of it? Oh, I know, I'm going to stick it through this wire. So basically, this capacitor discharges, you know, again, 180 degrees out of phase. It discharges into this inductor. And it'll keep discharging into that inductor until the field is fully charged. In other words, until this is out of current, you know, in zero. Okay, at that point, the current is not changing anymore, so the inductor is happy, and it says, hey, I got all this energy. Where can I get rid of it? Oh, I know, there's this capacitor over here. And it literally works, and this is what always confused me, but I realized that, you know, that really, until this capacitor is charged up, this inductor will keep dumping current into it, because an inductor, when you first, and this is why inductors resist, like this choke, resists a change in current, because when you first apply a voltage like 24 volts across this inductor, ignore the fact it's going to the center of this. If you just think about this battery being just shorted across this terminal and this terminal, this inductor has this voltage impressed across it, right, of 24 volts. Like, let's say this is positive and this is negative. Alright, well, because of that, the inductor itself actually forms its own voltage, kind of a back EMF of 24 volts, which prohibits current from flowing. So at first there's no current that flows through the inductor. It's got zero current flowing through it. But the voltage across it is really high. It's 24 volts. But partly the reason it's looked at as resisting the current is because it forms 24 volts inside the inductor, which is an opposition to this 24 volts that we're applying across it, right? So, and that's what keeps the current at zero. It's like you got one battery opposing, you know, this battery opposing this battery. But eventually, you know, again, based on an LR time constant kind of thing, okay, current does start to flow, and as it does, this voltage starts to decrease. And this happens very rapidly at first. That's why this magnetic field charges up very rapidly at first, but then it kind of levels off. So, you know, it's kind of a logarithmic thing. So, you know, the point is, though, is in 5 LR time constants or whatnot, the thing's fully charged up. Okay, but as that happens, once you hit the fifth constant, the time constant, you know, this thing is fully charged and there's no current changing in it anymore, but the voltage is zero inside this inductor. Now across it, it still has 24 volts across it, and you know, since it does have a resistance in it, you know, it's not a perfect, you know, inductor. You know, real wires have resistance in it. Because it's got resistors in it, it'll still have 24 volts across it with some maximum current flowing through it continuously. That's how you get an electromagnet. If you take a DC battery and hook it up to an inductor, you know, that has a you know, preferably an iron core in it, so it actually will amplify the magnetic field. It concentrates the magnetic field. But because of that, you know, at first that field has to charge up. So at first there's a real high current surge, but what will happen is it'll get up to some finite level and then kind of level off. Once this field is fully charged, there's still current flowing from the battery because it's DC, okay, but what's happening is that it's just eating up that power from that resistance in the coil. You're wasting power, but because you've got that current flowing through it, it continues to generate a magnetic field. And because it's generating a magnetic field, it'll act like an electromagnet. The problem is if you have a secondary on that, in other words, if it's a transformer, well, you won't see any voltage come out of it once it reaches that steady state. You'll see a voltage out of it only while the current is changing. In other words, while this field is charging up, you will see a voltage formed across the secondary of a transformer. But once it's done, you know, you hit the DC state, you know, once that field is fully charged up and it just is acting like an electromagnet, powered by a DC battery, well, there's going to be no voltage coming out of here. It's just going to sit there, with nothing. You can't tap into it because it's not, because you only get a voltage on a secondary of a transformer when there's a changing current on the primary. But if it's a steady state current, like an electromagnet, well, you're not getting any voltage out of it. So that's just a little aside on how inductors work if you don't realize it. Now, capacitors work, in a different way. They actually store energy in an electric field instead of a magnetic field. But once you take an uncharged capacitor and put a DC battery across it, the voltage on that capacitor will actually start out at 0. It'll be like a short circuit. So if it weren't for the fact it's got a resistance like you see here in series with it, it'd be infinite current. So you would see infinite, a very high current in practice, though, trying to flow through this to charge it up in the instant you hook it up. But that'll quickly fall off, and as the voltage increases across it, as this charges up, that current falls off dramatically. But as the voltage increases across it, and eventually it ends up being, the voltage on the capacitor ends up being equal to the voltage of the battery. Okay, and then you have energy stored there, so you can actually remove the battery, and voila, you've got power stored in this capacitor for as long as it, until it leaks away through its leakage resistance. So, or until you short its terminals out on something, or otherwise use the energy in some other way. Now, of course, in another video I was talking about how inductors don't really work that way, because they only store energy as long as there's current flowing in them. But I said you could, that's why you have a freewheeling diode on an inductor, because basically it tries to maintain the current flowing through it when you remove a power source from it, and basically the freewheeling diode allows it to do that. If you didn't have that freewheeling diode on it, there would be back EMF, or the flyback effect, in other words, which generates very high voltage across this, whatever voltage it takes to try to maintain that current flow. That's what I was trying to do. But at any rate, if you had some short circuit, like through a diode, it'll actually be able to maintain that current. But since it's through a real-world diode with real-world circuit resistance, it eventually dissipates all the energy in that field, so you can't keep it permanently stored like you can in a capacitor. Like if you had an ideal capacitor with no leakage resistance, you could store that energy in it indefinitely. Weeks or months, and even in a real capacitor you can store it for hours in a big electrolytic, and sometimes days in other more efficient capacitors. But inductors, you can't do that, because they have, you got to dump that, you got to maintain that magnetic field, and as long as you got that current flowing, you've got a magnetic field and you got energy stored in it. But once you try to remove that, this thing freaks out, and it will generate whatever voltage across that terminal, its terminals it can, and it's going to be reversed too, by the way. So if I had it charged this field up with positive here and negative here, well, in order to maintain that current, it tries to mimic a battery by forming a negative and a positive here. So it's actually in reverse, because it's actually trying to keep the current flowing in the same basic direction, and the way to do that would be for it to act like an external battery, and kind of form a circuit like that. So, but basically, the voltage it forms to try to maintain that current tends to be the opposite of what of what was impressed across it. So, it won't be positive here and negative here, which is how we charge the field up in our hypothetical coil, but it would be, negative here and positive here, so it actually reverses it. And that's key to understanding the oscillation in a tank circuit, because that's what happens. This, field collapses, okay? We have charged it up with a positive here and a negative here. Again, ignore this middle thing for this discussion. But basically, that charges this capacitor up with a positive here and a negative here. And this is why it's important to not use an electrolytic, at least a DC electrolytic, because you'll blow it up, because once this thing reverses, again, you got this plus and minus here. Well, once this is fully charged up, it'll start trying to dump its energy back into this magnetic field, okay, flowing in this direction, right? But now when that's depleted, again, this thing wants to keep the field, you know, the current flowing, so it reverses its voltage to where this is positive and this is negative, and basically it ends up charging this capacitor up in reverse. So this becomes the positive and this becomes the negative next time around. So, you know, that's a way of looking at it. And since we're charging in this circuit, we're charging it from the middle, you got to remember whatever happens in this coil, you can kind of think of it as happening over here too. So if you get, you know, let's say, you know, this is, you know, plus and this is minus on this coil, you know, which if this transistor were on, you know, this is connected to ground and this is your plus. Okay, you get current flowing through there, right? Okay, but you can kind of look at it as the same current is actually being induced into this circuit too, so you can actually look at it as whatever 24 volts you have here is doubled here. So this is 24 volts too, and it's in the same direction, so it's, you know, basically 48 volts. And you got to keep in mind too, just as a little aside, when you're winding a coil, you know, again, it's the direction you're winding it that's important in terms of which way it's turning. So if you turn it, you know, basically clockwise windings, you're going to get a different polarity in the magnetic field than if you go counterclockwise with the windings. So in these types of coils, they typically are all wound in the same direction. So if you're ever confused about that, like winding a flyback transformer or an induction heater, they all need, just think of it like a spring with a center, with a wire attached to the middle of it. That's what you need to do. You need to wire it like that. If you try to wire it like, okay, clockwise for half of it and then counterclockwise for the other half of it, the fields will actually cancel. So you won't actually form a magnet. It'll just be a wire with the fields canceling each other, which is an interesting effect, and it has its uses. You know, because you can actually control like fields inside a magnet by using another totally separate coil controlled by a totally separate circuit, because they are connected, and, you know, magnetically but not electrically. So you can do a lot of interesting things with transformers if you have a bunch of different taps on them, like you typically see in like a PC power supply transformer. So there's some interesting things you can do with shit like that. It's you know, it's a whole little area there. But the thing about it is that, you know, these things resonate because this keeps flipping voltage. This doesn't. You know, a capacitor doesn't flip voltage. When you charge it up, like if I put this battery across it and charge it to 24 volts, to be plus here and minus here, for example. Okay, you know, again, ignore the rest of this shit. If I just took this battery, you know, and plugged it across this capacitor, it would charge it up to 24 volts with this being positive and this being minus. Okay, well, you can discharge this capacitor all you want and it'll never flip signs. Every time you connect it up to the battery that way, it'll always be positive here and negative here. That's why you can use an electrolytic capacitor in a power supply, because that never changes. The only time it changes is if you flip this battery upside down and charge it in reverse. Then it changes, and then you blow up your electrolytic capacitor and have a really bad hair day. But generally, it doesn't ever flip the voltage. So in an AC capacitor, by the way, this is an interesting little fact, you know, in like the motor start capacitors and stuff, which actually are electrolytic capacitors, but the thing is that they're actually back to back, and they're in series with each other. So you have one electrolytic, you know, with its plus and minus here, but then another electrolytic with its plus but then minus here. So they're actually literally back to back, and one capacitor will act like a short circuit while the other capacitor acts like a capacitor, okay, in one cycle of an AC waveform. But when it goes negative, they switch roles. The other acts like a short circuit, and the first one acts like a capacitor. So that's how they work, and apparently that's how those AC capacitors work. They actually are back-to-back electrolytics. So although there may be a little more magic to it, so like, you know, resistors in series with it and crap that help level out those voltages. So, but the point is generally speaking, that is a way of creating a big, large value AC capacitor, but, you know, it will, of course, affect your capacitance. you know, you may have to put 2 capacitors in there, but you're never going to have more than 1 capacitance worth of storage. You know, so that's what kind of sucks when you see one of those AC capacitors that may have like a real high voltage to it, like 350 volts, but still it's only like 40 microfarads or something like that. But it's actually an 80 microfarad capacitor because there's 2 of them in there, but you can only use one of them at any one time because they're connected. I don't know if you can bust those open. I never busted one of those open. Maybe you can split it up. I don't know. I've never tried that. But I think they're oil-filled capacitors. That's why they don't. That's why they last quite a while, I guess. But still, those things do go bad. But anyway, the point is though is that that's kind of how resonance works. But now the real interesting bit, and you know the real kind of finale I've been trying to build up to, is the fact that after thoroughly confusing, I'm sure, myself and everybody else, is the fact that, okay, when this transistor is on, remember these 2 can't be simultaneously on or off at the same time. These diodes ensure that. That's what the diodes do. When this is on, this point here, well, hold on, let me run this simulation a little more so it's a little more clear. Okay, so when this is, wait, okay, yeah, when this is on, this is currently on, this transistor is on. As you can see here, its current is high, but its voltage is off. You know, the green is voltage, the yellow is current. So, but when this is transistor is on, okay, this voltage is very low. It's essentially ground. You can just think of it as being grounded. However, you know, when this is on, this is off, so that means this resistance is very high in this transistor, but that means the voltage can actually float up to whatever level, you know, is impressed across it. And I do use the word impressed across it because where does this voltage come from? It's 71 volts right now, and you can see that it's peaking, you know, at 69 volts or whatever. You can see where we're at in the waveform across this capacitor inductor, you know, parallel combination. Well, the voltage is coming from this. I mean, this capacitor or this inductor, you know, is at a point, you know, it's probably the capacitor, because that's, you know, but at any rate, you know, the point is the voltage across both of these right now is like high, really high. But you can look at it as the capacitor is charged up. The one thing I can tell you is that, you know, ask yourself this: where does this? Okay, this is a positive 71 volt wave, and this is a positive 71 volt wave, and it pisses me off. This is a bug in Falstadt that you can't get these 2 to look the same, even though they should be the same. I mean, this should be just as big as this, but for some reason you can't get it to fucking do that, piece of shit. But the fact of the matter is that you know, this is still always looked at as a positive waveform with respect to ground. Now, this has ground, okay, and then you got a capacitor here. Well, the thing is, that tells me, you know, that this capacitor, okay, has a positive voltage here and a negative voltage here. Alright, which you can see, you know, that again, that's kind of the case, because here's my positive sign. So I'm measuring this positive here and negative here. That's why this is a positive voltage, because of how I'm measuring it. Okay, well, that's what, you know, if you realize that this is connected to ground, okay, that means this voltage across this capacitor is with respect to ground. So that's like 69 volts above this voltage level here. So that gives us 71 volts, because remember, this isn't 0 volts, okay? This capacitor has like 69 volts across it. Again, more like 2 times 1.414, right? That's where that extra voltage is coming from. You know, the voltage across the actual capacitor is never more than 69 volts. So again, I think it really is 2 times the input voltage times 1.414. I think that's why it's approximately 3 times. I don't think it's because of pi. Incidentally, but the fact of the matter is that you know, this voltage here, you know, is on top of this ground voltage. So that's where it's 61 volts, right? because otherwise this thing's not connected to ground. I mean, this tank circuit you can consider independent. That's why I was talking earlier about how you could have this tank circuit just with a switch attached to it, and you could just disconnect the switch and it'll still oscillate. But and it doesn't have to have anything to do with ground. You can completely take the battery out; it'll still oscillate. So that is one of the epiphanies I had, is that this tank circuit actually is floating. And sure, it's connected to this like VCC circuitously, to the battery, but really it's not connected to ground at all. Again, ignore the secondary; that has nothing to do with it. Electrically, it has nothing to do with it. So, but what determines the voltage? Okay, we know there's a voltage across these components, but what is that? If I were to measure it with a meter, what would I measure it with respect to? Okay, I could put a meter probe across this, I would get 69 volts. But what would happen if I put it across ground? Well, if I measured it, across one terminal versus the other, you get a different result depending on where you're at. Okay, so if I had my meter probe, my black meter probe connected to ground, okay, my positive meter probe, and I measured here, right here I would get 1.7 volts, and right here I would get 71 volts. Why is that? Because this transistor is turned on. That is connecting this point in this capacitor inductor circuit. Again, ignore this. It's connecting it to ground. Again, ignore this, through the transistor. So, in other words, this is ground, and this is a 69 volt, the capacitor with 69 volts on it, with positive here and negative here, right? Okay, that's forcing this to be 69 volts, which is doing what to this diode? It's making sure that it's reverse biased, okay, because this sucker right here is 12 volts, but this is 71 volts. So no current's going to flow through this diode. So because of that, that allows this transistor to stay on, because this gate voltage is high. It's 12 volts. However, since this is at ground, alright, this right here is at 1.71 volts. Whereas this right here is at 2.5 volts. In other words, you take 1.71 and add a 0.7 volt diode drop to it. That gives you that, but that's not enough to turn this transistor on. So basically, it kind of keeps it off at a very low current the whole time. And if you actually look at the voltage, you'll find out it's not zero. Okay, see, this voltage is never zero, across this transistor. You can see all the parameters of the transistor when I highlight it. It's gate VGS, VDS, etc. But at any rate, it's never at zero. But the point is, this is effectively turned off when this is turned on, and vice versa. So but the thing is, in our current situation, you measure the voltage here. Okay, it's 71 volts and 0 volts. Now let's run the simulator to the negative side of it. Watch this waveform. Okay, now this is the point where they switch. Okay, and now we've gone to the negative peak. Okay, we got 69 volts, and you can see a negative sign there. Okay, so the fact of the matter is, if I measure it, alright, it's 1.5 volts we're getting. Why is that? Because this transistor is turned on and this one is turned off. And that's 68 volts. Okay, well, how are we getting 68 volts when this is saying negative 67? It's because this capacitor is now not charged up with a positive here and negative here. This inductor has actually, because of the energy going back and forth between these two, has actually flipped the voltage, okay, on this cycle. And again, it'll flip back later on, once the voltage goes this other direction. But for right now, as far as the transistors are concerned, and more importantly, as far as these diodes are concerned, this voltage, this is at ground now. Remember before ground was over here, but now ground is over here, and relative to ground, okay, since this is at ground, current can flow through this, okay, which does what to the voltage here? Instead of it being the 12 volts it needs to be, it's only 2 volts, so this is off. And since that's off, the resistance is very high through this transistor, and since the resistance is very high through the transistor, that means this capacitor voltage determines what the voltage is here. So, as a result, it's like 68 volts on top of the 1.5 volts we got here. So it's actually like 71 volts or so. technically, even though we're not quite getting that because it's not exactly at the same point. But the point is that this is a high voltage and this is ground, and since this is ground, current flows through here, which keeps this transistor off. But since this is a high voltage, well, no current flows through this diode now because it's got 68 volts here and 12 volts here. But since no current can flow through it, well, this doesn't siphon current away from this 10K resistor. So like it's doing here, I mean, this diode is short-circuiting this resistor, any voltage that was across it. So that's bringing the voltage down, turning our transistor off. Well, that's not happening here because this diode's off. It's not conducting. So that means this transistor's on because the diode's off. So because of that, this is at ground, and because it's at ground, we got a voltage on this capacitor which keeps the other transistor off. So it's the voltage on this capacitor relative to whichever transistor has ground that's keeping the other transistor off. So that is what's going on here with the oscillations. The oscillations, it's this voltage across this. And again, if the voltage on this capacitor is like 60 volts, the voltage across the inductor is also 60 volts. But just for simplicity, just think of it like the capacitor's got a charge on it, basically. So that just makes it, and really, that's probably what's kind of going on-ish, since, but at any rate, the voltage across both components is the same. So, but again, it's just easier to think of it as the capacitor being charged up as opposed to this inductor being charged up, because inductors aren't necessarily directly associated with voltage. I mean, the voltage can be variable. Yeah, this keeps switching directions, and when it does, again, it's relative to whichever transistor has ground, and it'll always be positive with respect to that. That's why it turns off. Okay, but basically, you can just think of it that this voltage keeps shifting first this way with respect to ground, and then this way with respect to ground. So it's either on this side of the ground or this side of the ground. But you can think of it as a capacitor. If you took a capacitor, let's charge it up to 50 volts, for example, where this is positive and this is negative, and we took that and stuck it here on ground where the negative terminal is always attached here. Well, okay, if it's pointed this direction, well then, this part of the circuit is positive, right? But then if you flip it over, okay, well, this could be looked at as positive down here too. You connect it to, a wire down here that makes it positive with respect to ground, and that makes this positive with respect to ground. Well, essentially that's sort of what's going on here, although that's, really, kind of trivial. You don't need two different wires, but it is from a charge standpoint if you look at it with respect to ground. So you can have two separate wires, and depending upon which one you connect the capacitor across, as long as negative is always connected to this, well, it's going to have a positive charge, or this one's going to have a positive charge. But again, it's always with respect to ground. Okay. But again, that's kind of a stupid way to look at it, but I mean, it kind of helps clarify it a little bit when you think of it, the fact that, really this capacitor is being connected to ground alternatively through this transistor being on, and then nextly through this transistor being on. So it's like you're changing, you've got, a value, a terminal, that actually is always being alternatively tied, to ground, but it's changing which terminal is tied to ground, and because of that, the voltage, across this capacitor is indeed like negative now, and it was positive earlier, but that's because we got our meter leads positioned this way. But here it's like the capacitor is actually being literally reversed every time this voltage changes side. So again, the voltage, or the transistor switch when this voltage is zero. It's a zero voltage switch. So, but this is the voltage that has to be zero to change the switch direction. Okay, but it does actually essentially reverse the capacitor when it happens. So even though this is like a negative voltage versus a positive voltage, it still is looked at like a positive voltage from the other transistor, because now instead of this lead being referenced to ground, okay, through this transistor, well, now this lead is referenced to ground through that transistor, you know, because they switch, basically, is what's happening. So they keep switching roles, and because of that, the capacitor keeps switching, and that happens to coincide where the capacitor changes its charge direction, because again, its voltage is always changing. But that's why this waveform always looks positive, you know. So it's positive 70 volts here and positive 70 volts here, but it's because this thing is continuously being switched back and forth. And that's what's critical to understand, and makes it hard to understand, because it's zero here, but when this voltage is low here, it's high here, okay? But in fact, one of these is a negative going side of this waveform, and the other peak is the positive going side. Again, it's hard to see because these damn things are disproportionate. You know, damn bug in this program. But you know, essentially that's what's going on. You know, one might expect to actually see a AC waveform, but remember, these are DC components, and since these capacitors keep getting switched, it's always looked at relative to one of these components. So relative to this transistor, okay, this is like got a voltage across it right now. Relative to this transistor, well, it has a voltage across it here, but no relatively low voltage here, and vice versa. So you know, when one has low voltage across it, the other has high voltage. It has low voltage across it because its resistance is really low and it's conducting current. So whereas here it's not conducting any current. Its current is practically zero, but its voltage is high. So, but these keep switching roles because, again, they keep alternately connecting either one lead or the other of this capacitor to ground, making the opposite lead of the capacitor show up as a positive voltage across its opposing transistor. So that's, again, sort of hard to kind of put it into words, but that's why I was trying to build up with all this theory, because if you don't have a lot of this understood, you can get really confused. And these are just things you kind of need to keep in mind, you know, in circuits like this. What makes it kind of complicated? But it really is really simple once you have that epiphany that, shit, this is just like a battery that I keep reversing the direction of, but that's why these diodes keep getting alternately blocked. You know, they're allowed to conduct, and when they conduct, a transistor is kept off instead of on, like you might expect. Okay, but then it's alternately blocked, and when it's blocked, the transistor turns on because this voltage is not short-circuited across this resistor. So it just goes back and forth and back and forth, and that's, you know, that's where you get this action. And but whose frequency depends on the value of this capacitance and the value of this inductance. So anyway, that's pretty much it in a very long nutshell. So anyway, I'll, you know, throw my explanation on the pile of shit out there trying to explain how these things work.